I am delighted to welcome to the stage Ian Buck, VP of Hyperscale and High Performance Computing at NVIDIA, for his keynote on advancing innovation in AI infrastructure. Welcome, Ian.
Well, good morning, everyone, and thank you to YJ. We spent a lot of time together. Building AI infrastructure is a challenging and brave endeavor. And building infrastructure that works not only a single rack, but an entire data center with that much compute to keep all those researchers active and busy and humming along is a challenge. And of course, as you know now, we're actually building those data centers, the next generation data centers, and every year we have a new platform and that's just the pace at which AI is going. So here at the AI Infra Summit, I wanted to talk through some of the perspectives of how NVIDIA thinks about this market, particularly around inference, which is a highlight and a focus of so many of us today. Inference is a pretty complicated landscape. Often people think of training as being hard. Certainly it's the 100,000 GPUs that we've just talked about, but inference itself has so many vectors of optimization and trade-offs people have to consider. There's the intelligence, how big of a model I want to deploy. It goes directly to the value of the model, but a bigger model costs more to run. The responsiveness of the model, how much compute should I put behind a particular model to make it more interactive, faster, more tokens per second for the user, or more tokens per second for my entire data center, are trade-offs that we can make on how much infrastructure, how much revenue versus how much experience I want to provide for every user. We have cost. Obviously, there's a litany of different hardware platforms, configurations from H100 to B200 to GB200 with GB300, and picking the right cost and the infrastructure we want to play into it and to build and run those models. There's a trade-off between throughput and tokens per second per user. I can serve a model with incredibly fast if I throw a massive number of GPUs at one query, but my data center generates revenue for all my queries. And that trade-off, the more I'm spending on one person's queries, the fewer total queries I can do for all the users. We have to think about our trade-offs in that Pareto. And finally, energy efficiency. Our data centers are measured not necessarily in square footage, but in megawatts or gigawatts. So understanding how much energy efficiency I can operate for a single model matters. All of these are trade-offs we have to make in our infrastructure and what we decide to build, and also our roadmap and how we innovate and think about the future. Hardware takes a long time to build. Silicon takes even longer. We have to think about all those trade-offs and project out a year, 2 years ahead in AI, which is nearly impossible. One of the most challenging parts of my job, to think about these trade-offs and make the right bets. At NVIDIA, another way of thinking about it is looking at this acronym which we call SMART. First, you have to think about the scale and complexity. What is the scale and complexity of the infrastructure you're building, and how can we make it scale and scale more efficiently? We have to look at that multidimensional performance. Every decision, we'll have to look at the different axes of how much intelligence, performance, throughput, cost, energy efficiency, and how those different metrics weigh into the final end solution for an AI factory. In the end, it becomes a full stack solution. You have the chip architecture, the rack, the node architecture, the rack architecture like you saw, but then the multiple layers of software and software optimization that go on top. All of that comes together to the solution. So that is it's hardware plus software that creates the total end throughput and performance. In the end, that delivers ROI. In inference especially, performance equals revenue. And I'll give some examples of how the math works there. But performance really is paramount to having the generating tokens, to getting those queries processed. And it is a performance to revenue, where training tends to be about capability per cost. And finally, all is happening not in a vacuum, but as a community. All of you here who are help building the AI infra of the future, many of you representing the companies that are building data centers or building hardware or building racks, connecting it all together and serving it, but also the open software community. YJ talked about OCP, open source software like OpenAI Triton, PyTorch, and the many other software stacks. All of these innovations are coming from the community. Unlike many of the other computer revolutions of the past, AI is particularly open, where researchers and companies are actually openly sharing their ideas, publishing their results, blogging about how to advance the future. And that's because it's a rising tide. As we all do that, we accelerate AI, we increase the opportunity for more AI, more models, more capabilities, which feeds a virtuous cycle. At NVIDIA, our contribution, again, is to continue to look at ways that we can increase the performance per watt per dollar, and as a result, turn it into profit for an AI data center. The most recent innovations and focus was around NVLink 72. We took what was originally a server box that had 8 GPUs that were NVLink connected of H100 or H200 or B200 and disaggregated it. We've moved NVLink out of the box and made it rack scale. An incredibly challenging endeavor. It built some amazing infrastructure that's being deployed now and being used now. We had to think and rethink about how we do Ethernet at scale. We want to scale up beyond the traditional 10, 20, 50,000 GPUs connected with InfiniBand to the 100 to million GPUs that want to be connected with Ethernet scale infrastructure. A very different kind of Ethernet, an Ethernet where every GPU or every node wants to talk to every other node at full performance. This is not what Ethernet was designed to do. It was designed to be able to connect clients with servers and it have a usage case pattern where it isn't everything talking everything all the time. That required a new kind of Ethernet, new kind of switch, and that's the basis for our Spectrum X Ethernet platform. Numerical methods. AI is a statistical problem. It's really just giving it data and producing a prediction. And using techniques, statistic techniques combined with numerics can open up the space of numerical representation. Everything started with FP32, 32-bit floating point, we all know. Google 10 years ago did bfloat 16. IEEE has now added FP8, which we support going all the way down now to 4-bit floating point. In fact, there's multiple 4-bit floating point formats. And recently we've been in Blackwell brought to market the NVFP4 format, which actually has micro tensor scaling to try to keep all these math, the entire AI operating in just 4 bits. To keep that statistically in range without things capping, we're constantly having hardware capabilities to keep the calculation totally in scale with constant biasing and rebiasing of the calculation. NVFP4 is being used for inference, and actually more recently, we've been able to figure out the numerical algorithmic techniques to do NVFP4, 4-bit floating point for training as well. This was recently announced in hot chips. Doing the math is easy, doing the numerics, incredibly complicated. Software is a big part of it. Of course, NVIDIA is just one contributor to the software ecosystem. Specifically, we released back at GTC, announced NVIDIA Dynamo, and I'll talk more about that. Our ability to take inference and disaggregate it across all those servers to be able to do context processing and generation and really scale up the number of GPUs we can assign to a single model requires an entirely new kind of software stack for serving models. In the end, this results in ROI. We have Blackwell delivers about 10 times the return on investment. This is comparing the amount of dollars you spend on infrastructure to how much you can generate in revenue in your AI factory. And of course, none of this happens alone. I manage teams that work on PyTorch with YJ, also JAX and other software stacks like OpenAI Triton, but also for inference. We have SGLang, VLM. NVIDIA has their own inferencing libraries called TensorRT LLM. All this is happening in a community, an open community, and by contributing and supporting and providing the foundational software for these technologies, or allowing researchers and developers or companies and clouds to be able to use it, we can elevate and bring all these technologies to market kind of in real time at a pace of, accelerating pace. It's quite amazing. Performance is a difficult thing to measure, particularly in inference. And, it's easy to make a claim, but how accurate is the model? I can take a model and I can run it in reduced precision. But if my precision isn't if I'm not delivering the same accuracy in a reduced precision format and running faster, I might as well be running a cheaper model. MLPerf is a benchmark that's been around for quite some time. In 2019, they started MLPerf Inference. This is where Google, NVIDIA, Meta, and many other companies in the industry come together, create a formula, we peer review each other's results to run benchmarks and actually prove that we can actually deliver a model with a certain amount of performance, with a certain token rate for a particular user, and agree upon that this is the established standard for measuring inference. Since 2019, NVIDIA has been submitting and running on all the benchmarks, going back to the Ampere architecture through Hopper to Blackwell. And, we've been continuously every year, delivering new benchmarks and rising the performance of AI models and inference. We hold every single per GPU record since the MLPerf data center benchmark started. In fact, this last round, which just gets announced today, and I think later on you'll hear from David Cantor, we've recently added DeepSeek R1, the new Llama 3.1 405B, and Llama 2 benchmarks were announced just recently on the new Blackwell Ultra or GB300 platform. This was used, we used the NVFP4, we used the Dynamo software, we used the new TensorRT, and we fully distributed the inference across the NVLink of the entire GB300 rack. In fact, the software to do all that is quite complicated. And literally since we've launched Blackwell last year to today, we have actually doubled the performance of Blackwell just with software alone. It's the complexity of how you distribute the communication, apply the new numerical techniques to improve performance, reduce cost, and get better throughput on MLPerf 2x in software on the same Blackwell totally for free. The same story played out in Hopper. We actually quadrupled Hopper's performance over its lifetime. The same Hopper 4 times faster just through software and applying all the optimizations by NVIDIA engineers, but more importantly by the open source community and researchers who are figuring out new ways to serve the same models at the same great accuracy, but just faster, cheaper, and generating more revenue. This is kind of the math that is today. Actually, a $3 million GB200 NVL72 rack actually will generate about $30 million in token revenue, to the point where actually a free GPU is not even cheap enough. If you kind of compare like let's say a previous generation or alternative platform with a quarter of the performance, you can see at the bottom there, the gray is actually the GPU cost and also the shell and server cost that all goes around it. If I even delete or remove the GPU cost, you can see that the revenue we generate over the course of multiple years is demonstrable. This is how we feel about inference. The performance of the platform is the revenue of an AI factory, and Blackwell literally delivers a 10x on what you buy to what you make. So let's talk a little bit more about inference and how it works, and where the innovations are happening right now in inference and what we're focused on. Inference is actually 2 different workloads. And on the left, on the right here, you get a query that comes in, and you do traditional inference serving. So then the first thing the AI model does is all the context processing. This is literally the question that you may ask a ChatGPT or a chatbot, but also all the other tokens that come in that are unique to you or the system prompt. So these are things that you've asked in the past, or things that are natural to your query that should assist the AI in answering the question that it's pulling from databases. It doesn't just look at your question, but all the other input tokens. That is called the context and prefill phase. And then after it's processed all the query and all the related data, all the input token, then it actually starts outputting tokens that you're reading. And that's the generation phase, or decode. Typically, we do this over a cluster of GPUs, depending on the model. It might be 4 GPUs, 8 GPUs, or even multiple GPUs, depending on the model size and the performance, but it's generally running one model across one set of GPUs. What's interesting though is that the context processing and the generation are actually different. They're both running the same model, but the context processing can be done in a massively parallel way. We can process all the input tokens in parallel, and where the generation of AI tends to be autoregressive. every token gets outputted, you have to run it again to calculate the next token, and in what's called an auto-regressive way, where processing 16K, 32K, even 100K input tokens can be processed in parallel. As a result, you actually have this performance delta where the context is very compute-rich heavy because we can do massively parallel, we can all do it at once, where the generation decode, because it's auto-regressive, needs a combination of memory bandwidth, NVLink bandwidth, and compute in order to fastly output numbers of tokens. If we stick on the same platform or one GPU, we end up having to pick the best of both worlds, but sort of in the middle somewhere, but not necessarily optimal for these two workloads. Today, most modern data centers actually do disaggregated inferencing. So they actually take that input query and they generate the context processing on separate GPUs, creating what's called the KB cache, basically outputs just the first token, and then it hands off the KB cache to another set of GPUs, which are optimized for generation. This allows us to actually split the number of GPUs we're doing for context versus generation, and actually and dramatically improve the overall performance. The NVIDIA Dynamo software is designed to do this. It's all open source. You can go check it out on GitHub. All of our development is GitHub first, so you can see live check-ins. But by doing this optimization, we can actually configure those GPUs and run the model with different AI kernels in a parallel compute context prefill way. And then for the auto-regressive part, configure it with different kernels, different parallelization techniques for the fast auto-regressive. This overall increases the total throughput, the same number of GPUs. And in fact, that will generate a 6 times improvement. Just for like Llama models alone, it's about 2 to 4, it's anywhere from 2 to 4x faster. Same number of GPUs, just doing disaggregated. It's a lot harder because you have to have two sets of basically workloads running in parallel on the system, and also having this KV cache transfer between the two platforms and keeping everything busy. We have, this is in production today. There's a company called Base 10, which is an inference aggregator, basically a model serving company. They have over 8,000 GPUs of both Hopper and Blackwell's spread around multiple clouds, including Google Cloud. They actually, when GPT OSS first launched, they had the fastest inference performance of any cloud provider because they super optimized using NVIDIA Dynamo that split between the context processing and the output generation. This is an important example of how much software matters in both and how it combines with the infrastructure of a rack like NVL72 and GB200. Overall, disaggregation gives you about 6 times faster first token on models like Qwen. We're seeing 3x higher, faster token output on models like DeepSeek, and basically turning inference into sort of a data center infra scale kind of problem. In addition to this, we're seeing that context processing becoming more and more important and higher value. Most of the models you see today can accept up to about 256,000 input tokens. And there's roughly, 2 to 3 tokens per word. So you can kind of get a sense of how much input token they can consume when you ask a question to a typical chatbot. But there's this slice of workloads that actually really love having super long input tokens. 2 examples of that is advanced codings. We've heard of coding chatbots basically to help you write code. Advanced coding chatbots take the entire program and use the AI to add new functionality. Instead of helping you write like a little loop of code or find bugs, advanced AI code is going to take 100,000 lines of code or 1 million input tokens of code and actually be able to output new functionality, entire code blocks, entire portions of the application to turn the AI really into a software agent that can interact with a software developer in a totally different way. But you need to be able to process literally millions of tokens, but the value is incredibly high because now I have basically a software developer that can amplify my entire software developer workforce by like 10x because the AI is actually generating the initial code that the developer can all work from at that kind of functionality scale. The other use case that's really hot right now is video processing and generation. Think of processing like an hour of HD video and producing new video content that's generated. Video is a lot of data, millions of tokens. Today, the video generation market is about $4 billion for AI video. And by starting the next decade, it's projected to be over $40 billion market. This is in the entertainment space and also in the media and marketing and advertising space. One way to think about it is, we used to live in a world where when we came home and watched on our TVs, it was whatever was on the TV. We moved to the digital era. Now we have on demand. We can watch whatever we want. And by the end of the decade, we're basically going to be on interactive media. It won't be whatever on demand we want, but all the interaction we could do for entertainment could be interactive, and of course will be done through video. So having these long context capabilities is really interesting. And whenever we see this kind of opportunity at NVIDIA, where there's a high value market with a place where we're pushing the limits, like how big our input context is, it's an opportunity for us to optimize further. So maybe there's a way we can actually process or work on these high value, large context instead, and maybe not use the same GPUs for context and generation, but focus on bringing these these new capabilities to market. And that's why we announced this morning, and here specifically at this AI conference, a new kind of Rubin processor dedicated for long context processing. This is the Rubin CPX GPU. It's a GPU specifically built for massive context length processing for these high value use cases of million scale token processing. It's specifically optimized for context processing and still, of course, CUDA capable. This is a new Rubin GPU, which we haven't disclosed or talked about before, based on the same Rubin architecture, but a new instantiation. It has over 30 petaflops of NVFP4, all CUDA capable. We've actually tripled down on the attention processing. Attention is the building block of many of the models we have today, and we actually have added new attention acceleration cores to this chip, which is 3 times faster than what we have in the current GB300 GPU. It is memory optimized. So a lot of the compute processing of context is compute rich. It's less dependent on HBM bandwidth or memory bandwidth, and less dependent on having NVLink scalability. So we can use the standard GDDR7 memory that we use today in most of the GPUs that are available in the market. And of course, we doubled down on video. So we added 4 NVIDIA video encoders and 4 decoders for processing and generating AI video content. And this will come online in the end of 2026, right after our initial launch and availability of NVIDIA Rubin. So how do you integrate this processor, this chip, this single die Rubin into the Vera Rubin rack? So here is Vera Rubin. We announced this at GTC this year. It has over 3.6 exaflops of AI performance in a single rack. This is coming be available in the second half of 26. As you can see, there's the compute tray. Each tray has 4 Rubins, 2 Vera CPUs, and ConnectX-9 for the scale-out interconnect. It's a pretty impressive platform. It's got over 3.3 times more compute in a rack than GB300, which is deploying today. It'll have 75 terabytes of fast memory and 1.4 petabytes of HBM4, and quite an impressive rack in itself. It all sits in the same rack architecture as GB300, to hopefully to help YJ and others here to deploy. It actually will fit in the same mechanical and space. And as you can see, 72 GPUs or packaged GPUs in a single rack. This is actually a dual die GPU, so it's 144. That's what we call it, NVL 444 Rubins in a single rack. But let's talk about CPX. We can actually just add CPX to this platform. In fact, right down the bottom, we have areas where we can insert additional the context processors and really boost this rack up for million scale token processing. This is the Vera Rubin NVL 144 CPX. All we have done here is taken the same tray, the same architecture, but we've inserted 8 of our Rubin CPXs behind the Vera in connection with the ConnectX-9s, And those processors are available for the entire rack to do context processing. I mean, just totally boosted up the performance of the rack. As you can see now, we're up to 8 exaflops, or 7.5 times what GB300 can do today. We've increased our memory again to 1.7 to 3x. Our fast memory has increased further to 100 terabytes. And again, all this will fit nicely into the existing rack infrastructure, so that for customers that want to prioritize Vera Rubin for million token input context, this is a seamless way to upgrade or integrate into their data centers. We also don't have to put the CPXs in the tray. We'll also be making a CPX-only compute tray version. And in fact, customers can actually just put it as a sidecar to their Vera Rubin rack. This is on the left, there's a new tray called VR CPX. As you can see, you have 2 Vera CPUs and 8 CPX processors connected with the same networking behind the scenes. And they can add a VR CPX rack in their data center side by side, either 1-to-1, 1-to-n, whatever their mix between their context processing and their output generation, where all the context processing is happening on the CPX rack and all the token generation can be happening on VR. And of course, 1-to-1 ratio is fine. They can mix it to 2-to-1, or they can start with some and expand later. All that makes it possible. You don't have to have them next to each other. The way context generation works is, as soon as you have your first token, you just need to send that KV cache to your token generators wherever they are in your data center. Quite an upgrade and running really fast. We've already been working with some of the Lighthouse customers who are super interested in long context. These are different AI innovators. We've all heard of Cursor, who's probably one of the leaders in intelligent code generation. And NVIDIA uses Cursor along with many others. And this will help them get to the next level of developer productivity with those million input token code generators. Magic actually, as a magic.dev, has 100 million token input model, quite impressive. And we're working with them to figure out how to get that working on CPX, along with Runway, and which is a company which generates cinematic video, and other leading inference providers like Fireworks and Together AI, who have some of the most advanced techniques for the fastest model serving and how they can get to that next level of million token inference. So we've added another chip to our roadmap. You can see here we have in Blackwell, we have the Blackwell and Blackwell Ultra, the Grace CPU, our NVLink switch chip, the Spectrum 5 switch, and of course the CX8 NIC. All of these chips come together to make AI and AI infra work. It's never just one chip, it's a family. And now with Rubin, we've added the CPX processor, a different Rubin GPU dedicated to and optimized for context processing that'll be paired and matched with Rubin for the million scale context processing, and fits nicely into the full family. And of course, that'll extend, and we look forward to talking more about Feynman when we get a little bit closer. All of this has to come together. The AI is not served, and data centers aren't built with one processor. They're connected machines. They require CPUs. They require GPUs. They require various levels of accelerating. The network and infrastructure at scale needs to work as one in order to serve these models and bring that token value and that revenue that inference will generate all together in one. And that's what we're focused on at NVIDIA, is bring all that infrastructure and the baseline software stack to market as quickly as we possibly can. One challenge, of course, is how do we build those future data centers? I've shown you a lot of racks, we've shown a lot of chips. The next challenge, of course, is what is that future data center going to look like? YJ talked about how the CPU data centers have evolved and how they're so different. And NVIDIA is also a huge proponent of open standards. We're members of OCP. We've contributed the GB200 rack to OCP, and we'll do so for the upcoming infrastructure as well. But the problem now is becoming a data center scale one. How can we build and provide, and working with the community, a data center roadmap, not just a rack and GPU roadmap, that's going to be designed for the future, that allows us to scale and grow? It's pushing the limits of power generation, mechanical, plumbing, electrical, bus bar design, row length, CDUs. And how are all these pieces and components going to work together in order to run and have these data center factories work well and be future-proofed as we scale out, not just for Vera Rubin, but Vera Rubin Ultra and going on to Feynman. We've started a new initiative called the AI Factory Gigascale Reference Design. And of course, NVIDIA isn't doing this by ourselves. We're working with the entire community from Cadence to Emerald AI to ETAP, GE Verona, Jacobs, which is the main engineering consulting firm that builds a lot of these data centers, Schneider Electric, Siemens, and Vertiv to build the cooling, plumbing, and electrical systems that can scale to deliver this kind of future data center in a way that take a long time to build and need to have a reference architecture. All these components need to talk to each other. The CDUs and the power and the data center operations have to work as one, along with the GPUs and compute infrastructure, so they work seamlessly and maintain uptime and high efficiency. Working with these partners now, and we expect to have the first version of the reference design done in our next upcoming GTC conference. That's my update for today. I thank you, everybody. It was really exciting to launch CPX here at AI Infra, and look forward to the rest of the talks.